Okay, students, so let's get started with today's video. Today we are going to do topical past papers for A2 related to the topic of alternating current. This is your chapter number 10. Chapter number 10, topical past papers. Let's start with that. So let's see question number 1. A circuit contains a power supply, okay, that provides a sinusoidal input voltage. Okay, basically you have a sinusoidal input voltage. There is an output voltage across a load resistor as shown in figure 7.1. Okay, there is an output voltage across this resistor. Okay. State the purpose of the circuit shown in figure 7.1. So basically, this circuit does what? This circuit is used for rectification, or you can say full wave rectification. You can write it is used for full wave rectification, rectification of AC voltage, or you can say of alternating voltage into direct voltage. It is basically used to rectify alternating voltage into direct voltage. Simple as that. Okay, let's move on to part B. Let's move on to part B. Figure 7.2 shows the variation of output voltage with time. Okay, you are given the variation of output voltage with time. Okay, that's perfectly fine. The load resistor has a resistance of this. Okay, so your resistance of the load resistor is this. The maximum power dissipated in R is this. Okay, so this is your maximum power. Let's write down things. Your maximum power, we have to show that it is equals to 0.22 volts. We have to prove this or we have to show this. How will we do that? We will say that maximum power is equals to what? V naught square over R. What is V naught? V naught is your maximum voltage. Okay. Or you can say peak voltage. Both are correct terms. Maximum voltage or peak voltage, both are correct terms. So let's move on to the graph here. What is your peak voltage here? If I zoom in a bit, I think this is a too much. Let's see. This is your peak voltage. Somewhere here, this is 9, your peak voltage. Okay. V naught is equals to 9 volts. Okay. So let's put 9 here. 9 square divided by what is your resistance? 370. It comes out to be 0.22 volts. Simply we have proven this. On figure 7.3, sketch the variation with time t of the power dissipated in resistor R. So basically we have to draw a graph of power versus time. So first and foremost thing, go to the voltage output graph and look for the points where your voltage is 0. At time 0, at 2 point, at 0.02, at 0.04, at 0.06, and at 0.08 seconds, your voltage is 0. That means at these points, your power will be 0. So let's mark these points. At point 0, you will have a power of 0. At a time of 0.02, your power will be 0. At a time of 0.04, your power will be 0. At a time of 0.06, your power will be 0. And at a time of 0.08, your power will be 0. And now, do one more thing. Can you see these middle points? These points? 0.01, 0.03, 0.05, 0.07. At these points, you have the maximum voltages. If you have maximum voltages at these points, this means what? At these points, you will have maximum power at these 4 points. What was the maximum power? 0.22. So let's mark it here. So your maximum power will be here, 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 and here. Let's connect all these dots like this. Let's connect all these dots like this. 1 second. Like this. Yeah. Once you connect all these dots, you will have power versus time graph. Okay. Now you have to calculate mean power. Okay. So do you guys remember the formula for mean power? Mean power used to be equal to what? Maximum power divided by 2. What was your maximum power? 0.22 divided by 2. Your answer comes out to be 0.11 volts. Okay. Let's move on to part C. The circuit in figure 7.1, okay, is disconnected and R is connected directly across the power supply. Okay. Explain without any calculation how the mean power now dissipated in R compares with the answer in BI3. Okay. So now basically see what is happening. Now, basically, what you have done is you have removed all these diodes and your circuit looks something like this. This is your voltage input, and you have connected a resistor with it like this. You have connected a resistor with it like this. Okay. What will happen? Although now, although now your voltage output, although now your voltage output graph will look something like this, a sinusoidal curve, but still your power graph, but still your graph of power versus time will remain what? Still your graph of power versus time will remain what? Same as the one you have drawn earlier. Can you see if you connect the resistor directly, your voltage output graph surely changes because now you will have both negative and positive voltages. But your power graph will remain same. This graph will remain same. So what will you write here? Power time graph remains same. Hence, hence your mean power, hence power mean remains same. Okay. And now if anyone is still confused that how will your power versus time graph remain same? So what was the formula for power? What was the formula for power? VU square over R. Now even if you put a negative value of V, it will get squared and give you the same positive power VU square over R. So either your voltage remains positive or negative, your power will come out to be positive. So I hope this simple mathematical trick was clear to you guys. Let's move on to the next question. Marking schemes are attached in this PDF, and in this PDF is basically linked in the Google Drive ka link I have shared in the description below. Okay, let's read out this question. An electron in a metal rod moves randomly about a mean position. Okay, an electron is moving about a mean position. When an alternating voltage is applied to the ends of the rod, the mean position can be considered to oscillate with simple harmonic motion along the axis of the rod. Okay. Figure 4.1 shows the variation with time t of the displacement of the mean position. So this is the displacement versus time graph. Okay. You have to calculate the amplitude of oscillation. Okay. Now, this is not a normal graph. This is not starting symmetrically from zero. This is not a graph like this. So you can't just read off the scales. You can't just read off the scales. Whenever your graph is non-symmetric around the y-axis or x-axis, how do we calculate the amplitude? To calculate amplitude, we use this formula. Amplitude is equals to the maximum position minus the minimum position divided by 2. Okay. So here, if I zoom in, what is your maximum position? This value. This will be equal to what? 7.2. What is your minimum position? This value, that is 0. So let's see here. Maximum is 7.2. Minimum is 0 divided by 2. This gives you an answer of 3.6. And always remember to include the unit on the y-axis. That is 10 raised to the power of minus 15 meters. Okay, so let's write it here. Your amplitude comes out to be what? 3.6 into 10 raised to the power of minus 15 meters. Simple as that. Also, one more thing that you must know right here is if you have to calculate the mean position, if you have to calculate the mean position of a graph starting non symmetrically, you will say maximum plus minimum divided by 2. Okay, here my maximum value was 7.2, minimum value was 0 divided by 2. My mean position comes out to be 3.6. So my mean position will be somewhere here, somewhere here, this value. Okay, I guess that's correct. Yes, this is 3.6 line. Determine the angular frequency of the oscillation. Okay, we have to determine the angular frequency of the oscillation. Very, very easy. If you can notice here, if you can notice here, let's say, let's take the most obvious points. If you can see here, this peak is starting at a value of 0.15 and you get the second peak. Your first peak was at a value of 0.15, your second peak is at a value of 0.35. What is the time difference between one peak to another peak? What is the time difference between one peak to another peak? 0.2 microseconds. So this will be your time period. What will be your time period? Your time period is 0.2 microseconds. Okay. Can you calculate the angular frequency? Yes. W is equals to 2 pi over T, 2 pi divided by T, that is 0.2 into 10 raised to the power of minus 6. What will your answer come out to be here? Can anyone tell me the answer? 0.2 into 10 raised to the power of minus 6. What will your answer come out to be? Yes, 3.1 into 10 raised to the power of 7 radians per second. Okay. Use your answers from part AI and from AI2 to show that the maximum drift velocity of the electron is this. Okay. So this stems from the simple harmonic motion chapter. If you have to calculate the maximum velocity, what will you do? You will take the amplitude, multiply it with W. What was your amplitude here? 3.6 into 10 is the power of minus 15. 3.6 into 10 raised to the power of minus 15. What is your value of W? Your value of W is 3.1 into 10 raised to the power of 7. If you multiply both of them, you will get an answer of 1.1 into 10 raised to the power of minus 7 ms minus 1. Simple as that. Let's further move ahead. Okay, let's see this question. The rod has a cross-sectional area of this. Okay, this is your area and contains a number density of conduction electrons. Okay, these are your number of electrons. Let's say they are represented with n. All of the conduction electrons in the rod may be assumed to be oscillating in phase with and with the same amplitude as the oscillation in figure 4.1. Okay. Use the information in part I3 to calculate the magnitude of the current in the rod. So this basically this is an AS level question. Current is equals to what? NAQ V. What are your number of charges? 8.5 into 10 raised to the power of 28. What is your area? 4.3 centimeter square. This is a centimeter square. Whenever you want to go from centimeter square to meter square, what do? You multiply by 10 raised to the power of minus 4. Multiply by 10 raised to the power of minus 4. What is Q? The charge of electron. 1.6 into 10 raised to the power of minus 19. What was the velocity of electron? As far as I remember, 1.1 into 10 raised to the power of minus 7. Yes. 1.1 into 10 raised to the power of minus 7. You can put this in the calculator and you will get an overall answer for current as 0.64 ampere. Simple as that. Let's move on to part I2. On figure 4.2, sketch the variation of current I in the rod with time t between t is equals to 0 and 0.4 microseconds. Okay, so we have to sketch the graph of current versus time for time t is equals to 0 till time t is equals to 0.4 microsecond. How will we do that? How will we do that? So if you come here, you will realize that the time period of this wave is zero point 0.2, 0 0.2, 1 second, 0.2 microseconds. So you need to complete one wave within zero point 0.2 microseconds. So basically you have to draw two oscillations. So you have to draw two oscillations. Up till now, that is clear. Now, if you move further, if you go further, you will realize one more thing. If you move further, you will realize one more thing, that I can write, I can write this current as what? NAQV. This is a traditional formula for current. But I can also replace velocity like this: change in displacement over change in time. Because velocity is what? Displacement over time. This formula will help me a lot. This formula will help me a lot. Let me show you how. Let's take this formula to the top side. This is going to help me a lot. 1 second. Yes. So if you see here, at these points, at 0.05, that is this 0.05, at this point, that is 0.15, at 0.25, and at 0.35. You will notice that at these 4 points, if I draw a tangent here to calculate the gradient, I will get a gradient of 0 because this is a horizontal line. If gradient is 0, that means what? Change in x over change in t is equals to 0. That means if change in x over change in t is equals to 0, I will be equal to 0. That means my current at these points 0.05, 0.15, 0.25 and 0.35 is 0. So first of all, let's mark that. I have gotten a very important conclusion here. Here my current will be 0, current will be 0, 0 and 0. Okay. Now let's further visualize this again. Now if you look at this closely, you will realize that at these points, at these points, at these points, you are at what? At these red points, you are at the mean position. At these red points, you are at the mean position. You are at the mean position. Okay, let me create some space here. I guess we are short on space. So let's do one thing. Let's move this towards the let's move this towards the right hand side. Okay, so at the red markers, at the points that I have marked in red, we are at the mean position. And do you remember one thing from simple harmonic motion? Do you remember one thing from simple harmonic motion? At mean position, at mean position, your velocity is maximum. Okay, so if this term gets maximum, my current will get maximum. Okay, so at these specific points, that is at time 0 and what were the other times? Let's see, 0 0.1, 0 0.2, 0 0.3 and 0 0.4. Okay, 0 0.1, okay, 0 0.2, okay, 0 0.3 and 0 0.4, you have maximum values. In my opinion, you have more than enough points to draw a graph. You can start drawing like this. Something like this along these lines. Okay. And Oh, actually, my drawing is really, really bad. Apologies for that. I am a very bad drawer. Uh, let's see this. Okay, these are your curves. Basically, these are what? These are cosine curves. These are cosine curves. Okay, let's move on to part I3. Use your answer in part A2 and B1 to determine an expression for current in terms of t. Okay. So just by looking at it, you can see this is a cosine curve. So we can write it like this. I is equals to I naught cosine WT. What was your I naught? 0.64. What was your W? I think we calculated that as well. Your W was 3.1. Okay, so 3.1 into 10 raised to the power of 7 multiplied by T I is equals to this. So this is your final formulation for I. Now you have to calculate the root mean square of the current. So basically IRMS is equals to the peak value of current divided by the under root 2. So your peak value of current was what? 0.64 divided by under root 2. Your answer comes out to be 0.45 ampere. Let's move on to the next question. A varying current I passes through a resistor of resistance R in the circuit shown in figure 7.1. Okay. Basically, a varying current is passing through this resistor. Okay. We are shown the current versus time graph. Okay. The current has a magnitude of 2 I naught. Okay. If you see, the current has a magnitude of 2 I naught when it is in the positive direction, and it has a magnitude of I naught, you can see here, when it is in the negative direction. Okay, the period of the variation of the current is t. Okay, the current is varying with a period of t. Okay, determine in terms of I naught and R the power dissipated in the resistor when the current is in the negative direction. Okay, so if the current is in the negative direction, what will your power be? Power is equals to negative I naught square into R. This comes out to be what? I naught square R. Okay. When you are in the positive direction, what is your current? 2 I naught. Okay. So if your current is 2 I naught in the positive direction, what will be your power? 2 I naught square into R. This becomes what? 4 I naught square into R. This is your power in the positive direction. Okay. Let's further move ahead. Let's see. What do we have to do next? On figure 7.3, sketch the variation of power with time from t is equals to 0 till t is equals to 2 capital T. Label the power axis, okay, within appropriate unit. Okay. So basically, we have to draw the graph of power versus time, and we have to label the axes of power. Okay. So what we can do here is we can say that five boxes five boxes on these y-axis represent I square r, and other five boxes will give us a value of what? 2 I naught square r, and other five boxes will give us a value of what? 3. Okay, so this is a bit misplaced. Let's do it here. 3 I naught square r, and these last five boxes, if we add them up, our value will be 4 I naught square r. Okay. Now, if you closely see here, for the first 0 to 0.5 t, your current is in the negative direction. If your current is in the negative direction, your power is I naught square r. So your line will look something like this. Oh, why have I drawn an arrow? Uh, Something like this. Yeah, maybe like this. Okay. And when you are going from 0.5t to 1t, when you are going from 0.5t to 1t, you can see you have a positive value of current. A positive value of current means that you will have a power of 4 I naught square r. So let's make that as well here. 4 I naught square R. Simple as that. Okay. And then again, if you reflect, as you are going from 1t to 1.5t, you are again having negative current. You will again have a power of 1I naught square R. And from 1.5t to 2t, I have already seen that you have a positive current. So you will have a power of 4I naught square R. Something like this. Yeah. And let's join these horizontal lines with vertical lines like this. Something like this. Like this. Like this. And since I'm really bad at drawing, this is taking me a lot of time, but you guys will be able to do it in 30 seconds maximum. Yeah. Okay. So use your answer in part B to determine the expression in terms of I naught and R for the mean power. Okay, you have to calculate mean power. How can you do that? Very easy. Power mean can be calculated as what? Power minimum plus power maximum divided by 2. What is your minimum power? I naught square R. What is your maximum power? 4 I naught square R divided by 2. Your mean power comes out to be what? 2.5 I naught square R. Okay. Now let's move on to part I2. Calculate the root mean square current in the resistor. You have to calculate IRMS. You have to calculate IRMS. How will you do that? You now know the mean power. You now know the mean power. You know mean power is equals to what? IRMS square into R. What is your mean power? 2.5 I naught square R is equals to IRMS square R. R and R will get cancelled out. Let's take an under root on both sides. Take square root on both sides. What will happen? 2.5 I naught square under root is equals to IRMS square. This square and this square will get cancelled out. This and this square will get cancelled out. Only 2.5 under root will remain. I naught is equals to your IRMS. Simple as that. Now let's see the marking scheme. Yes, the marking scheme is also telling us the same. Let's move on to the next question. 4 diodes are used in a bridge rectifier circuit. Okay, bridge rectifier circuit is basically a complicated name for rectification. To produce rectification of a sinusoidal AC input voltage. Okay. Figure 7.1 shows part of the circuit, but 3 of the diodes are missing. Okay, 3 diodes are missing here. Okay. The potential difference across the load resistor is the output potential difference of this bridge rectifier. Okay, this is your output. Okay, state the name of the type of rectification. This is what? Full wave rectification. How do I know that? Because there are places for 4 diodes here. Full wave rectification. Okay, let's move on to part 2. Complete figure 7.1 by drawing the 3 missing diodes correctly connected. Okay, let's draw the 3 missing diodes correctly connected. So I can easily see that this input, okay, one journal knowledge thing here, journal knowledge or recap, you can say. No, it would be better if I term it as a recap. One recap here should be that input terminals are always connected to the opposite ends of the diode. Okay, what do I mean by that? If your diode, your first diode key line is connected here, the triangle or the positive terminal of the second diode will be connected here. Okay, so let me recap it, or let me bring in a picture here. I think that would work fine here. One second. Let me bring a picture here. Just give me a moment. Yeah, something like this. Okay. Always remember, always remember. Let's recap some things here. Always remember that your input terminals always have unlike terminals of the diode. One negative, one positive. This is connected to the input. One negative, one positive. This is connected to the input. So your input terminals are always connected to the alternate or unlike terminals of the diode. Here we had a negative, so here I had to put a positive. Similar will apply for the downside. Similar we will do for the downside. Something like this. Something like this. These are how we will mark your four diodes. Okay. On figure 7.1, draw an arrow to indicate the direction of current in resistor R. Okay, so you have to indicate the direction of current in resistor R. Okay, let's say this is positive, this is negative. Okay, the positive current will start to travel from here, it goes from here, goes from here, goes from here. So your direction of current is towards right like this. Your direction of current is towards right like this. Simple, simple logic. Nothing complicated here. The input voltage has an amplitude of V naught and time period of T. Okay, the input voltage has an amplitude of V naught and a time period of T. Okay, figure 7.2 shows the variation with time T of the input voltage. Okay, so this is the variation of input voltage with time T. Okay, let's see what the examiner is asking. On figure 7.3, sketch the variation of output voltage with time with t between t is equals to 0 and t is equals to 2t. Okay. So basically we have to tell how the output voltage will vary between time t is equals to 0 and 2t. So whenever we do rectification, what happens? The negative cycles become positive. The entire graph remains the same. Okay, so let's do that. Let's do that. Let's do that. First of all, let me confirm and zoom in here. This point. The graph is becoming 0 at which value? 0.25t, that is half. Okay, 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 okay. So let's do one thing. This will be here. You will have a 0 here. And when you have a negative peak, see, you have a negative peak at 0.5t in the input voltage. But in the output voltage, this negative voltage will get converted into positive. So at 0.5t, you wouldn't mark a point here. You will mark a point here. And again, let me see at, okay, we have something like this. At middle point, we have again a value of 0 like this. Then we have a maximum value. Then a 0 like this. Then a maximum value. Then a 0 like this. And then a maximum value. So let's draw the graph. Somewhat like this. Okay. Somewhat like this. Simple as that. This is your graph for the output voltage. Obviously, this is not drawn with a pencil, so it is very untidy. The power dissipated in the resistor is P. Okay. On figure 7.4, sketch the variation of power with time between t is equals to 0 till time t is equals to 2t. Okay, so now we have to draw or sketch the graph of power from time t is equals to 0 till time t is equals to 2t. Okay, how are we going to do this? Very, very, very easy. Again, as we have done earlier, at all these zero values, at all these zero values of voltage, okay, we will have zero power. So let's mark them. Oh, one thing that I can do here, I can minimize this so that both of them come in one screen, and 1, 2, 3, 4, 5, a 0 point here. Uh, 1, 2, 3, 4, 5, a 0 point here. Okay. 1, 2, 3, 4, 5, a 0 point here. 1, 2, 3, 4, 5, a 0 point here. Okay. So at all the points where the voltage is 0, you have your power as 0. And where will the powers be maximum? Where your voltages are maximum. At time t is equals to 0, 0.5, 1, 1.5, and 2. Okay, at all these points. 1, 1, 0.5, and something like this. Okay, so let's start drawing the graph. Something like, oh, that's pretty untidy. Pretty untidy with respect to my standards as well. Okay, and let's do it like this. Okay, so this is your power versus time graph. Obviously, this oscillation is a bit crooked, so let's draw it again like this. Let's draw it again like this. Okay, let's further move ahead. Suggest with a reason how the root mean square RMS value of voltage output compares with the RMS value of voltage input. So this is your voltage output graph. This is your voltage input graph. Can you see both of them have the same peak value? Can you see both of them have the same peak value? Or you can say, or if you are a very good student, you can say both of them will have the same power graph. I have explained this in the first question. Even though if you put a negative voltage, your power will come out to be same. So you can say both of them have same power versus time graphs, power versus time graphs. Hence what? Hence the VRMS remains same for both. Remains same for both. Okay. Let's move ahead to the next question. Okay. Figure 5.1 shows four diodes and a load resistor of 1.2 kilo ohms connected in a circuit that is used to produce rectification of an alternating voltage. Okay. State what is meant by rectification. Okay. That's very easy for 1 marks. Converting voltage into DC voltage, into DC or direct voltage. Anything works fine. Here, for 1 mark, you don't need much. Okay, state the type of rectification produced in figure 5.1. This is full wave rectification. Full wave rectification. Okay, let's further move ahead. Let's see the next one. A sinusoidal alternating voltage Vin is applied across the input terminals X and Y. The variation with time t of input voltage is given by this equation, okay, where Vin is in volts and time t is in seconds, okay. On figure 5.1, label the output terminals P and Q with appropriate symbols to indicate the polarity of the output voltage. Very easy. Let's say this is the positive, let's say this is the negative. Positive charge starts to go from here. At this point, it reaches a decision point. From where should it go? From a forward bias diode or a reverse bias diode? This is a forward bias diode, this is a reverse bias diode. It will obviously go from a forward bias diode like this, like this, like this, like this. As it reaches Q first, Q will become positively charged, P will become negatively charged. Simple as that. Let's further move ahead. The magnitude of the output voltage varies with time as shown in figure 5.2. Okay. On figure 5.2, label both of the axes with correct scales. Okay, we have to mark the scales. Use the spaces below for any working that you need. So the y-axis scale is pretty easy. So the maximum voltage is 6. Okay, so if you come here, maximum voltage is 6. If you zoom in here, you can say that this is 0, this is 4, this middle point will be 6, this will be 8. So you can erase this 6 value as well. And you can say on y axis, every 10 boxes represent 4 units. Okay, for the x axis, I guess we will have to do some amount of calculations. On the x axis, we have time. Okay, so this thing is what? Your W. So let's bring it downward. 25 pi is equals to your W. And what do we know? W is equals to 2 pi over T. Can I calculate the time period? Yes, surely I can. 2 divided by 25. My time period comes out to be what? Time period is equals to 0.08 seconds. Okay. So basically, this means that my time in this yellow highlighted region here is 0.08 seconds. Okay, now let's see how can I approach 0.08 here. One thing that I can do is, let's say I assume that every 10 boxes on the x-axis represent what? 0.02 seconds. This will be your axis like this. 0 point, this will become 0.1. This is 0.12. So this is how you mark the axes. So let's move on to the next question. The output voltage in B is smoothened by adding a capacitor. Okay. So basically these fluctuations in voltage are smoothened out by adding a capacitor. Okay. The difference between the maximum and minimum values of the smoothened output voltage is 10% of the peak value. Okay, what does this mean? What does this mean? This means that if your peak value is, let's say, 6, your maximum drop is 5.4. If your peak value is 6 volts, your maximum drop, yeah, you can say, you can better phrase it like this. You can say the minimum value, yeah, minimum value after applying a capacitor will be 5.4 volts. Now, in the circuit currently drawn, you can see you have a maximum value of 6, minimum value of 0. It is fluctuating between 6 and 0. But when you apply the capacitor, your peak value will become 6, minimum value will become 5.4 volts. That is 10% of the peak voltage. On figure 5.1, draw the circuit for a symbol of a capacitor. Okay, let's draw the capacitor here. That will be in parallel to this resistor. Something like this. This will be your capacitor. Okay, let's further move ahead. And on figure 5.2, sketch the variation. Oh, this is a very good question. You have to sketch the variation of the smoothened graph. Now, how will you do that? You know that the minimum value is 5.4. Okay, so let's first of all locate 5.4. This is 4. This will be 4.4, 4.8, 5.2, and 5.4 will be somewhere here. Yeah, in the middle of this. So, somewhere here. You can say, you can say that as you move, you will have to draw these lines carefully. Okay. So, first of all, the examiner hasn't told you to draw this line, but you can do that. You can draw this upward line as well. 1 second. Yeah, something like this. And then what you will do is you will take a point at the peak value, you will take a point at 5.4 volts and make a curved line like this. Yeah, like this. And then again, take a point at 6 and take a point at 5.4. somewhere here and draw a line like this. Oh, draw a line like this. This would get pretty easy once you have a pencil. And like this. Okay. And yeah, you will leave it like this. You will leave it like this. Yeah, this graph will be left like this. So what have I done unique here? I have drawn these lines. These lines carry important marks. Why? Because these lines tell you that your minimum voltage drop this time is what? 5.4 volts. It is not reducing down to complete zero. It is going down to only 5.4, and from 5.4 it is again recharging to a peak value. So this was a good part. This was a unique and a different part. So chalo, let's further move ahead. Calculate the capacitance of the capacitor. Okay, that's very easy. What will we do? V is equals to V naught E minus T over tau. So at the starting, your voltage was 6. After some amount of discharge, it became 5.4. What was the time taken to do this? What was the time taken for this? Let's see. It is starting at 0.02 and it is ending somewhere here. This is what? Let's see. This will be 1 second. 1, 2, 3, 4, 5. This will be 0.05. This will be okay. So this point is 0.054. Okay. So your starting value of time for discharge is 0.02 and your ending value is for discharge 0.054. So what is the time difference, or you can say time here? 0.034. Okay. So let's put it here 0.034. And in place of tau, what can you put? Resistance into capacitance. Do we have the resistance already? I think we have the resistance already. I have read it somewhere. 1.2 kilo ohms. Yes, it is 1.2 kilo ohms. So we have the resistance. We have literally everything that we need. 5.4 divided by 6 is equals to E minus 0.034. Resistance is 1.2 into 10 raised to the power of 3 multiplied by the capacitance. Can you calculate the capacitance by manipulating this equation? Yes. What will you do? Take Ln on both sides. Take Ln on both sides. Okay. Then you will have an Ln of 0.9 is equals to Ln E minus 0.034 divided by 1.2 into 10 raised to the power of 3 multiplied by C. Ln E gets cancelled out. Okay. So we have what? Ln 0.9 is equals to negative 0.034 divided by 1.2 10 raised to the power of 3 multiplied by C. I have to calculate C. So let's make C the subject here. C is equals to negative 0.034 divided by 1.2 into 10 is the power of 3 multiplied by ln 0.9. You just have to put this value in the calculator and you will get your final answer. That comes out to be 2.7 into 10 is the power of minus 4 farads. Simple as that. This marks the end of the past papers for alternating currents. If you have any ambiguities, you can ask in the comments below, and the PDF document for this is attached in the description. So, thank you for watching and take care.